We are given two complex ions and we are asked which one's paramagnetic, diamagnetic, high spin, low spin, larger splitting energy, etc. So first of all, we want to start just by identifying the type of orbital that we would be drawing. And since this is an octahedral complex ion, we know that we will be drawing an orbital splitting that has this kind of drawing. So top will be EG with 2 orbitals and bottom will be T2G with 3 orbitals. And we will have to draw the arrow for splitting energy, which looks like delta O, meaning the splitting energy for an octahedral complex. Okay, so now we have to figure out how many electrons to add in here. And that will depend on the metal's electron configuration. And since water is neutral, nickel is just going to be 2+. Then we have to find out the electron configuration. And by the way, sometimes they might give you an exception, such as chromium, copper, gold, silver. Those are so they are exceptions where instead of 4s2, they write 4s1. Okay, so nickel 2, 4, 6, 8. It's gonna be a 3d8, and I removed 2 because this is a 2+. That means we have to fill in 8 electrons. Now, how do we fill it in? That will depend on water, the ligand. Water is a weak field ligand, so that means the splitting is rather small, so the electrons can fill the higher level as well first before filling the orbitals in pairs. So 8 electrons to 4, 5, 6, 7, 8. Okay, so we got this done. And another question that they might ask you is, based on this ligand, what kinds of wavelengths will it absorb? Well, since it is a weak field ligand and with a small splitting energy, that means a weak field ligand will absorb a longer wavelength. Since we can think of it as this, it's a weak field, so a longer wavelength means weaker energy, right? So that's why it has a small splitting energy, because it absorbs long wavelengths, which have low energy. So longer wavelengths, and that will be like red, orange, etc. Let's just say red. So since this is absorbed, that means it's actually reflecting something opposite, like green. So this complex is going to be green. Okay, now let's compare it with this other example. And we'll go through the same procedure. This is octahedral because it has a 6 coordination number. And then we want to figure out what kind of splitting to draw. And since it's octahedral, we'll draw the same splitting with 2 orbitals on EG. And because this ammonia is a strong field ligand in comparison to H2O, the splitting is going to be a lot larger between these 2 orbitals. So our arrows for the splitting energy is going to be longer. And then nickel, in this case, let's see, ammonia is also neutral. So it's also nickel 2+ here, which means we'll use the same configuration with 8 electrons to add. Now the difference here is how we add the 8 electrons. So that will depend, once again, this is a strong field ligand. So that means there is a large splitting energy. If there's a large splitting energy, that means electrons are going to have a harder time adding themselves to this higher energy without first filling all of the lower energy orbitals, which means we're going to add all 8 of our electrons to fill the bottom first before filling up the last 2. It just so happened that these 2 configurations now look the same, although that's not always the case, so you want to be careful that strong field ligands, you're adding the electrons in a different way. Now, what is a possible color for this complex ion? So once again, the observed color is going to be the opposite color of the color that actually absorbs. So since it's a strong field ligand, that means it must absorb a high energy. That's why we have a higher splitting energy. So a color with a high energy means it has a short wavelength. So short wavelengths could be like blue. So if it's absorbing blue, that means it must be reflecting something like orange or yellow. And there you have it.